You know, vision transformers, they're the absolute powerhouses behind so much of today's AI vision. But what if I told you that a core piece of these incredible models is actually fundamentally super fragile? So today, we're going to dig into a fascinating paper that uncovers this hidden weakness in self-attention and, even better, reveals a really elegant, innovative fix.
So think about it this way. What if the very thing that gives these AI models their powerful sight actually has a massive blind spot? I mean, we always hear about the self-attention mechanism, right? It's celebrated as the source of their power, but this new research suggests it might just be their biggest vulnerability.
All right, so let's get right into it. To really get what's going on here, we've got to peek under the hood of these vision transformers, or ViTs as we'll call them.
So if you look at a typical ViT, it's basically built with these repeating blocks. Each block has two main parts, something called a self-attention block, or SAB, and a feed-forward network, or FFN. And crucially, they also use these things called skip connections. These basically let the input take a little shortcut around a block and get added back in later. Now, that might sound like just a boring design detail, but trust me, we're about to see just how critical one of those little connections really is.
Okay, so this self-attention block, this is where the real magic happens. This is the part that lets a model look at a whole picture and figure out, okay, what's the most important stuff to focus on here? It's pretty much considered the key ingredient to a vision transformer's amazing success. But, and this is the absolute bombshell, right from the paper's abstract, that star player, self-attention, completely falls apart without its trusty sidekick, the skip connection. And look, we're not just talking about it getting a little bit worse. The word they use is catastrophically. That's a huge deal. So what actually happens when you put this to the test? Well, the researchers ran an experiment to find out exactly what breaks when you pull that connection out. They did something really simple, but kind of brilliant. They just asked, hey, what if we just take out that one little skip connection that goes around the self-attention block? And whoa, the results are pretty dramatic. Just look at these charts. The blue bars show a normal model's accuracy. The yellow bars, that's the same model, but with that one skip connection removed. Performance completely tanks. It's not just a small dip, it's a total failure. And it points to a weakness that seems to be unique to self-attention. So how bad are we talking here? Well, on the CFAR-10 dataset, just removing that one connection made the model's accuracy crash by about 22%. 22%. That is just massive for taking out one tiny wire, so to speak. And you know what? It gets even worse. When they moved up to bigger, more complex datasets, the model without that skip connection didn't just do badly, it completely failed to train at all. The whole training process just broke. This isn't some minor quirk. It's a sign of a deep, fundamental instability. Okay, so the big question is, why? Why does this happen? Well, the paper digs into the mathematics to find out, and the answer, it turns out, lies in this idea called ill conditioning. Let's break this down real quick. You can think of a condition number as a way to measure how stable a system is. A low number is good. It's like a solid, sturdy table. You can lean on it, no problem. A high number is bad. That's a super wobbly, unstable table. You definitely wouldn't want to put your coffee on that, right? For a neural network, you want that table to be rock solid. Okay, now check out this graph from the paper. See that blue line way up at the top? That's the condition number for the self-attention block without its skip connection. It just skyrockets. We're talking values over 1 million. That is one extremely wobbly table. The other lines, which all have skip connections, are way, way lower and so much more stable. I mean, this right here, this is the smoking gun. And just to really drive this home, let's compare the two main parts of the block. When you take the skip connection away from self-attention, its condition number explodes. But if you do the same thing to the feed-forward network, its condition number is only around 1,000, much, much more stable. This explains exactly why taking out the FFN skip only causes a small dip, but taking out the SABs is a complete disaster. It really shows you that self-attention by itself is just fundamentally mathematically unstable.
So, okay, we've found the problem. Self-attention is basically a wobbly mess, and this is where the paper gets really cool because they introduce their big innovation. It's a brand new fix they call token graying.
So you can think of skip connections as a great reactive fix, right? They swoop in after the wobbly self-attention part and stabilize everything. But these researchers asked a totally different question. What if we could make the inputs more stable before they even get to the wobbly part? A proactive solution.
And that's exactly what token graying does, using a method called a discrete cosine transform, or DCT. It's basically a three-step process. First, it breaks down the image data into its core frequencies. Then it boosts the weaker, high-frequency signals, all the fine details, to create a more balanced signal. And finally, it puts it all back together into a new, more mathematically stable input. It's kind of like tuning a guitar before you start playing instead of trying to fix the sound afterwards.
So, does it actually work? Well, this chart says it all. A big yes. The bar on the left is the stability of a standard model. The next two bars show what happens when you add token graying. You can literally see the number going down. They're making the system measurably more stable.
And this is so important because it creates this really clear link. Better math, which leads to better stability, leads directly to better performance. It's that simple.
Okay, so let's zoom out. What's the big picture here? Why does an insight like this really matter for the future of AI?
Well, this table really brings it all home. It shows the accuracy for several different, really advanced vision transformer models. The middle column is their normal accuracy. The next column is their accuracy with token graying. And what do you see? Across the board, every single one gets a little bit better. It's a consistent, measurable boost in performance, and it all comes from just understanding the math a little bit better.
All right, so let's boil it all down. What are the big things to remember? First, self-attention is the star of the show, but on its own, it's mathematically unstable, super wobbly. Second, those skip connections aren't just a neat trick, they are absolutely essential to stop the whole thing from collapsing. Third, new ideas like token graying prove we can do even better by making things more stable from the start. And finally, getting these deep foundational ideas right is how we're going to build the next generation of smarter, better AI. And that kind of leaves us with this one last thought to chew on. We just saw how a component that most people probably took for granted, that little skip connection, was actually way more important than anyone knew. I mean, it really makes you wonder, right? What other essential parts of our AI models are just sitting there, hiding deep secrets and new opportunities that we just haven't even thought to look for yet?